For decades, we have searched for the best technology to power our modern lifestyle and enable clean technology like electric vehicles. Since the early 90s, the battery technology of choice has been lithium ion. It powers everything from phones and Teslas to energy grade backup facilities and even satellites. But despite the fact they have brought us into the 21st century, they have some severe downsides. This is where lithium sulfur battery technology becomes interesting. A technology that was constrained by several challenges in the past is now being solved by the R&D community that will make it a good substitute to lithium ion battery technology with exceptional KPIs. We have spread the entire webinar across these 5 sections. Collectively, they will provide insights across why the emergence of lithium sulfur battery technology matters to various industries, businesses, and society. The webinar sheds light on key technological advancements on lithium sulfur battery technology and how close lithium sulfur batteries are to commercialization and who are the key entities actively. Battery technologies hold the key ingredient for transitioning away from fossil fuel dependence. Within the next 10 years, energy storage can transform numerous industries. Rechargeable batteries with a high round trip efficiency are crucial for energy storage for many applications. They can accelerate the shift towards sustainable and smart mobility, help supply clean, affordable, and secure energy, and mobilize industries for a cleaner, circular economy, including whole life cycle assessment. Unsurprisingly, battery demand is rising dramatically across all applications, majorly demanded by the mobility sector. Asia, specifically China, is expected to dominate battery demand growth by 2030 as more people switch to electric vehicles. Battery demand growth is inevitable as the energy transition quickens, but global supply will fall short without substantial investments or improvements in battery technologies in the immediate future. In addition to the rapidly rising demand and undersupply market, the industry is facing trade wars and unprecedented events such as the global pandemic disrupting the supply chain of essential materials. For example, the need for rare earth battery raw materials owing to rapid mobility electrification in China. In addition, the recent price hikes of lithium carbonate, an essential material for lithium ion batteries, and large corporations' pledges to reach carbon neutral have put more pressure on the currently available battery supply chain and the overall ecosystem. The market for rechargeable batteries is currently dominated by lithium-ion batteries, which perform well in most applications. However, current generation lithium-ion batteries are approaching their performance limits in applications, for example, heavy-duty commercial vehicles or passenger ferries. One of the vital specifications of battery technologies, that is, energy density, is limited to up to 500 watt-hour per kg. These have been the limitations to electrifying weight conscious, high power applications such as passenger aircraft. Further, the costs of new generation batteries are already competitive with the current prices of lithium ion. With slow progress in electric vehicle driving range and smartphone endurance, the limitations of current lithium ion batteries have become apparent. First commercialized by Sony in the 1990s, the now dominant lithium ion technology is struggling to improve the performance of the existing chemistry. Its incremental gains are outpaced by the consumer demand. So, what's the catch? Why don't we already have them in the commercial market today? I will invite my colleague Deepak to throw some more light on some of the potential challenges and how these challenges are being addressed by various key entities in the ecosystem. Over to you, Deepak.
As far as evolution of lithium sulfur batteries are concerned, the LIS concept has been kicking around since the 1970s. However, the poor endurance and safety prevented its commercialization until now. Low life lithium sulfur batteries were deployed in the aerospace applications, offering high unit densities as the application demanded such needs. Uh, Recently, developments from the researchers and nanotech experts from Monash University It includes a new solid electrolyte and the use of nanocomposite material that protects sulfur from electrolyte contact, and it have nearly realized the goal of a lithium sulfur battery. It survives as many charge cycles as lithium ion and also meets the flammability regulations of various markets. Currently, the industry is witnessing lithium sulfur batteries with both high energy density as well as a life cycle of up to 4,000 times. So, how does it stack up against the current holy grail, which is the lithium-ion battery technology? Lithium sulfur battery's most significant advantage over any other counterpart battery technology is their substantially higher energy density per unit weight. Reducing the cost of batteries is also one of the biggest challenges which are being faced by various manufacturers. Much of the cost of the current batteries is due to the expense of metals, including nickel and cobalt. In contrast, the materials used in the electrodes of lithium sulfur cells are comparatively low cost, with sulfur being amongst the most abundant element on Earth. In terms of the life cycle, developments and announcements from Monash University, Drexel University, CSIRO, and other innovators last year have seen promising reports of capacity retention of up to 1000 plus cycles. So, in summary, lithium sulfur is a clear winner in terms of key specification. However, a scalable approach for material design that aims at cells with low electrolyte volume or high electrode loading is a vital and is a fundamental challenge for lithium sulfur battery technology, which is being addressed by the R&D community.
We will talk about how what is expected in the future in terms of opportunities and threats around lithium sulfur batteries. Where should the battery technologies be by 2035, and what are some of the associated opportunities around lithium sulfur battery technologies itself? From 95% recyclability to almost double battery life, industries are anticipated to have strong and specific requirements from future battery chemistries. It is also worth noting that current generation lithium sulfur battery prototypes are 3 times as energy dense as lithium ion and could charge just as fast. Battery degradation is a severe worry, particularly for the EV world. Second-hand EVs can sometimes be useless if the battery is spent, which will cost a small fortune to replace. Overall, this is slowing EV adoption, and that implies that electronic waste, which is already a considerable problem, will only worsen in the future. While lithium-ion batteries will continue to play a major role in the energy storage landscape, disruptive ideas are required that can enable the creation of the sustainable batteries of the future. In view of all of this, lithium sulfur battery technology will gain further traction from commercial launches of batteries for aircrafts and EVs. Lithium sulfur battery technology is also eyeing the consumer electronics segment market, which is expected to be 5 billion USD by 2030. However, merely just 5% of the lithium ion market, which is expected to be around 200 billion USD by 2030.